அனைவருக்கும் வணக்கம். Today we are going to discuss the domain theory of ferromagnetism. So, what is this domain theory saying about the ferromagnetic material? This is a thing we are going to discuss today. Actually, in ferromagnetic materials, if you look at the interior, the spins are aligned parallel to each other. But in what way it is arranged means. So, I want to draw the one simple diagram. If this is the ferromagnetic material, if look at the cross sectional view, we are not looking into 3D directions. So it's separated into different region. The ferromagnetic material, it is separated into different region. These are the small region. Within the small regions, if you look at the spin of the all the electron, it will be aligned parallel to each other. That is called spontaneous magnetization. So this small portion, it is called the domain. So within this first domain, all the spins are aligned in the particular direction. That is called spontaneous magnetization. If you look at the another domain, the nearby domain, these spins are also aligned parallel to each other. So these domain spins are spontaneously magnetized, but the nearby domain spins are aligned one direction. The next domain spins are aligned another direction. So they are not parallel to each other. So within this domain, all the spinors are parallel, but the nearby domain spins are different from the first domain spins. So if you look at this domain, in this domain, the spins are aligned some other direction. If you look at this domain, the spin may be aligned this direction. Suppose if you look at this domain, the spin may be aligned in this particular direction. Suppose if this domain spins are aligned in this direction, suppose this domain spins are aligned in different directions. So once if you are like zooming the ferromagnetic material, there is a spontaneous magnetization. So the first point you can just collect from the domain theory of ferromagnetism. There is a spontaneous magnetization. Spontaneous magnetization within the domain. That means each domain is having the spin. So those spins are spontaneously magnetized within the domain. So each domain spins are randomly arranged. So each domain spins, that means the each individual domain spins are arranged in parallel, but the spin of the resultant spin of the particular domain is different from the other spin of the other domain is different from the spin of others domain. So this is the second point we can notice from this diagram. The third point you can make. The third point what you can notice here means there is a spontaneous magnetization in all the domain, but the resultant magnetization is zero because each domain resultant spin arranged randomly. So the resultant spin of each domain, resultant spin of each domain arranged randomly so that resultant magnetization is zero. Resultant magnetization is zero. Each domain spontaneously organized, but the resultant spin of individual domains are randomly arranged, so the resultant magnetization is zero. Because if you look at the first domain, the resultant spin is this direction. If you look at the second domain, and the resultant spins are this direction. If you look at the third domain, the resultant spins are the downward direction. So if you sum up all the domain spin, the resultant spin goes to zero. So hence, when we are not applying any external magnetic field, the net magnetization in the ferromagnetic material is zero. So that's the thing the third point is conveying to us. The fourth point, if you look at that one, the first domain is separated from the second domain by the some boundary. This boundary is called the domain wall. So this is called domain wall. So you can make the small point. The domains are separated by the boundaries is called domain wall. So we can ask the next one question: how we can magnetize this ferromagnetic material? That is the next question we can ask. So how we can magnetize? How we can magnetize there are two ways we can magnetize the ferromagnetic material. The first method by domain wall movement, by domain wall movement. The second method by domain spin rotation. By domain spin rotation. First, we will look at what is a domain wall movement. How we can magnetize the ferromagnetic material by the domain wall movement. So, by domain wall movement. First, we need to draw the domain structure. Here, simply I am drawing this domain structure. Suppose if you take this is your domain cross-sectional view. If you have simply four domains like this, these are the domain walls inside the ferromagnetic materials. The first domain, the spins are aligned in the upward direction. The third domain spins are all the spins are aligned in the downward direction. I'm just drawing the red arrow that shows the resultant magnetization of the each domain. The top domain, its spins are aligned from left to right. The bottom domain, right to left. So the top and the bottom will cancel with each other. The right and left, the domain magnetization will cancel with each other. So the resultant magnetization of this domain goes to zero. Suppose if I'm now, this is in general it is true when the external magnetic field, if it is zero, that means there is no external magnetic field. Now the same domain I am taking, the same magnetic material. Now what we are going to give, I am just applying the external magnetic field. That means external magnetic field now it is not equal to zero. So what you can observe here means the domain ball move. How it will move means, suppose if you are applying the external magnetic field in this direction. So which domain spins parallel to the external magnetic field, that domain ball it will be enlarged or it will move. So if I look at that one, because the first domain spins, the resultant spin or all the spins are parallel to the external magnetic field, so that ball will try to move. So this spin now it will be strongly magnetized with the external magnetic field. So other spins it will be slightly displaced due to the slightly it will lose its memory due to the domain or moment. So only the parallel spin domain it will grow larger. So there is a micromechanism will be there. I don't want to go into the detail. So this is the domain by the domain wall movement. It will get magnetized with the ferromagnetic material. Now we are going to look at by domain spin rotation how it's going to magnetize. So the second point we are going to see by domain spin rotation. You can just draw the diagram. Now what you can do, you can draw the, suppose if you are giving the external magnetic field, but here we are giving the weak magnetic field. So this weak magnetic field enough to move the domain ball. Suppose if I am giving the strong magnetic field, what I am going to give, if I am applying the external magnetic field. So what it will do, suppose I am applying the external magnetic field to this direction. So what it will do, the parallel spin will grow, the parallel spin domain it will grow stronger as well as larger. The other spin, what it will do, it will just try to rotate along the external magnetic field. That means if you look at this spin's domain, it will just try to rotate. It will try to rotate, or it will try to rotate along the strongest external magnetic field. So this is a way if your ferromagnetic material get magnetized, this is called the domain spin rotations. So the first one is weaker magnetic field. The domain wall movement is happening because of the domain wall movement. The domain spin parallel to the external magnetic field, it will grow larger. So this is a way if your ferromagnetic material, if it is getting magnetized, that is called a domain wall movement magnetization. The domain spin rotation magnetization of the ferromagnetic material, how it will happen means, if you are giving the stronger external magnetic field, the spin of the each domain it will try to rotate along the external magnetic field direction. So if your magnetic material getting magnetized by this way, this is called the domain spin rotation magnetization. So thank you all.